This video is the first of multiple videos on algorithms that involve traversing graphs. To understand this video, you need to be okay with the material on definitions of graphs and of graph searches, which is presented in the slide set entitled Graph Search Intro, which is not a video. This first video is on the category of searches and graphs that work in the order called breadth-first search, abbreviated BFS. In that, when we are at a particular node, we traverse to all of its adjacent nodes before traversing to any of the nodes that are adjacent to the immediately adjacent nodes. The problem we are dealing with is to find shortest paths in a graph. In particular, given an undirected graph, a graph whose arcs are bidirectional, and with n nodes, n vertices, and a designated source vertex S, we want to find the shortest paths from S to each of the remaining vertices. The length of a path, like this one, which has unweighted edges, unweighted arcs, the length is simply the number of edges on the path. The problem, then, is to find those paths from S to each of the other vertices, which has the smallest number of edges on the respective paths. The brute force solution would be to enumerate all paths without cycles, all simple paths, starting from S. And then for each pair, S and some target, some destination vertex, to choose that one, that particular path that was shortest. That, unfortunately, there may be as many as n factorial simple paths in a graph. So this brute force approach might take order n factorial time, well more expensive than we can afford. So we need a better solution. Let us say this idea of breadth-first search to produce these shortest paths, say it symbolically and more precisely. We're given a graph G with a list of vertices, capital V, and a list of edges, vertex pairs, that are connected. And we're given that one of those vertices within V is the designated vertex S, which is the source of all our paths. Breadth-first search systematically explores the edges. It discovers every vertex reachable from S, and as it does, it computes the shortest distance. It also yields the paths with root S that are all these shortest paths. One way to think about this is for any destination vertex V, it allows you to trace path back from child V to its parent, and from that parent to its parent, and so on, eventually getting back to S, and thus yielding the full path from S to V. It does this systematic exploration in so-called breadth-first search order. That is to say, it looks broadly from a vertex. That is to say, looks at all of the vertices that are attached to it before it looks at any paths from those vertices to other vertices to which they're connected, which might be considered as grandchildren of the original vertex. Search algorithm colors every vertex. We will initially color all the vertices white. They have not been discovered. That is to say, they've not yet been examined at all. When we first examine a vertex, we will color it gray. We've begun examining it, but we've not done examining it. When we have finished examining all the nodes adjacent to a gray node, then we will color the formerly gray node black, meaning we've seen all of the adjacent nodes. As soon as a vertex is examined, we'll be able to give it a path length, and we'll do so. In this algorithm, we keep a queue of nodes to be extended from, and initially we put S on the queue, and that's the only element on the queue. As we examine other nodes, they will be put onto the queue. That is to say, at the end of the queue. We'll also be keeping track of path length, and the path length for the node S will be recorded as 0. The algorithm works by taking each node from the queue and put its undiscovered adjacent nodes on the queue. Undiscovered meaning it's either undiscovered meaning it's not gray and it's not black. That is to say, it's white. We'll be marking the new nodes as discovered. We've seen them now. And we'll be incrementing the count from that of its parent, the node it was adjacent to when it was put on the queue. So increment by 1, and then assign that to the new nodes. So for example, the nodes adjacent to S will have path length 0, the distance to S, plus 1. The newly discovered nodes will also be put on the results tree, which we'll call pi, and the paths from the node that we're dealing with right now to its adjacent node that we've just discovered will be labeled as an arc in the tree. We will keep doing this, taking nodes off of the queue, putting others at the end of the queue, until the queue is empty. Finally, when all of the nodes from any if you take a node off the queue and are processing its adjacent nodes, or more precisely, its adjacent undiscovered nodes, formerly undiscovered nodes, once we've dealt with all of those nodes adjacent to you, we'll mark you as black, that is to say, as complete. Most easily understood with an example. Consider the graph that we see on the screen now. Initially, it will have a designated node S whose path length from S to it is 0. We see that S has 3 adjacent nodes, the ones colored in the discovered color. We will successively examine each of those nodes, and as we examine it, we will color it discovered, and we will take S's length, 0, and make the path length to these newly discovered nodes 0 plus 1, so they will get path length 1. Once we've done this for all of the 3 nodes adjacent to S, we will give S the finished color. This is the state shown in the left graph. After we've got all of the adjacent nodes to S discovered and their path length created, and thus arcs from S to each of them marked as tree arcs for the tree that has S as its root. Moreover, when we have reached this stage, S is no longer on the queue, and the 3 adjacent nodes are in some order on the queue. Now we see the state when each of those formerly discovered colored nodes have been taken off the queue, and for each of them the adjacent elements have been put on the queue. So let us, for example, consider the node just directly above node S. It had been labeled as path length 1. It has 4 adjacent nodes, S and the one immediately to the left of it, the one immediately to the right of it, and the one immediately above it. S is already finished, so it's not formally undiscovered. So we don't deal with that one, but we deal with the other 3. For each of them, we take the node that we're dealing with, namely the one immediately above S, look at its path length, which was 1, and give the newly discovered 3 nodes path lengths of 2, and the respective paths from them, the 3 paths, will be marked as tree paths. We also deal with the, for example, the diagonally left node of S. It is attached to, adjacent to, S plus 2 other formerly undiscovered nodes, which we will mark as discovered. Those are the 2 diagonally to the left of S. The 2 colored in this middle example graph as discovered. They also get their path incremented from the path length of the one directly adjacent to S and diagonally to the left. If that path length was 1, so the other 2 get to be 2. They get put onto the queue. So at this point, the queue has 5 things on it. The 3 above S, these 2 and these 2 in addition. And likewise, we mark the arcs as tree arcs. We still are dealing with the node that is immediately to the right of S. And we look at the nodes adjacent to it. One of them, up and slightly to the right of it, has already been discovered. One slightly to the below and slightly to the left of it has also already been discovered. And, of course, S itself has been discovered. So there's only one additional node adjacent to it to put on the queue, the one diagonally to the right of it. That is to say, it's the one going from S diagonally to the right and then diagonally to the right again. Its path length is likewise taken as 1 plus the path length of the thing it came from. And as we have completed dealing with each of these 3 nodes, that is to say, have reached all of its formerly undiscovered nodes and put them on the queue, we respectively mark each of them as complete. So by the end of this process, shown in the graph, all 3 nodes adjacent to S have been marked as complete. And all of the discovered nodes, in some order, are on the queue. In the final stage, we go from the elements in the queue one by one to their adjacent undiscovered nodes. Each one of them is adjacent to something with a path length 2. So its path length is 2 plus 1 for all of these additional nodes. Their path lengths are 3. The paths to them, whichever one was found first, is marked as a tree arc. So, for example, for the node to the lower left, it could have been discovered from the node above it or the node to the right of it. And whichever one was found first will have marked it as discovered, and that path will be marked as a tree edge. And when the other node that's adjacent to it looks at it, it will have already been labeled as discovered, and so it will not be marked as a tree edge. So at this point, all the nodes that in the middle graph, middle version of the graph, were marked as discovered, now they have all been marked as complete because all their adjacent undiscovered nodes have been put on the queue. And the queue consists of the 5 nodes marked as discovered in the rightmost version of the graph. We take each one of them off the queue and find that there are no adjacent undiscovered nodes for each of them. And so after all of them have been taken off and then colored, finished, the queue will be empty and we stop. Here is the algorithm that we have described. We begin in steps 1 through 4 to color all the nodes, all the vertices. I'm using node and vertex as synonyms. We color all those vertices white. That is to say, as undiscovered. We set the length to each node, each vertex, to be infinity, and we have the connections from each node to any other node that's going to form the tree to be nil. And this loop loops over all the vertices, and we have this initialized situation. We proceed with our initialization to color S gray and to set its distance to 0. And to say the tree connections of S are, the branches from S are not yet specified. We empty the queue and then put S on it. Now we're set up to do the loop, successively taking elements off the queue. That begins with line 10. We keep within this loop until the loop is empty. If it's not empty, we take the front element of the queue off, and we look at all of its adjacent elements. Only if the adjacent element is undiscovered, that is to say, if its color is white. So if the adjacent element V is white, then we want to do some things with that. And what we're going to do is to color that adjacent element gray that we've discovered it. We have its distance be 1 plus the distance to U from which we came. And we have a branch in the tree between V and U. And then we also put this adjacent element V at the end of the queue. When we've done that for all adjacent undiscovered elements to U, in line 18, we color U black as being complete. It's the end of the algorithm. Let us go through another example. A graph with 8 nodes shown in item A here. One of them, S, is the source node. In this example, we will not only notice the breadth first order that's developed and the path lengths, and indeed the whole process, but we'll emphasize the marking of the branches that form the paths that we're developing from S to ultimately to each of the other vertices. And arcs that are part of the path and then form the tree pi will be marked with broad gray lines. When we start, S has been put on the queue. The queue was initially empty, but the first step puts S on the queue. And it has been given a length 0, and it has been marked as discovered. The loop of the algorithm then begins by taking off the head of the queue. There's only one element on the queue right now, namely S. Taking it off. And in part B, we see that the 2 nodes that are adjacent to S, namely W and R, have been put on the queue, W then R, and each of them has been marked as discovered, gray, and each of them has had its path length from S stored as the length in S, where we came from, to W and R respectively, plus 1, and thus path length of 1 from S to W and from S to R. And the arcs are appropriately made gray. Also, once both W and R have been dealt with, S is now marked as black complete. Or I guess as white, it's called. Anyway, it's shown as a black background with a white letter, white numeral. Notice that we could have, by happenstance, dealt with R first and W next, in which case the Q would have R as its head and W as tail, and that would have been equally okay. But let's work with the order which is illustrated, namely W was first put on the Q and then R. At this point, we're done dealing with the with the nodes adjacent to S, and we go back and take something off the Q at the head, namely W, leaving R on the Q. And then in figure C, we see that the two vertices adjacent to W, but previously undiscovered, have been put on the Q. So after R, which remains on the Q, we've put T and then X. We also examined the connection from W to S, but S was not undiscovered. In fact, it was complete. So we do not put that on the Q. We did not deal with S further. The path links to the two things that were now discovered in marked gray, T and X, are set as one greater than the path length in W, which is the node that we're processing as the base node right now. And so they're given the value 1 plus 1, 2 in both cases. Moreover, the arcs from W to T and from W to X are made tree nodes, part of the paths. What that means is that if you want to go from S to X, for example, you would follow the path to W and then from W to X, namely those marked paths that are shown here. Okay, so now our Q has R and T and X on it, and we take off the front item in the Q, namely R, leaving T and X. And when we look at R, we see that it's connected to S, but S is already complete. And it's connected to V, and V is not yet discovered. In this figure D, we see that V has now been marked as discovered. Its length has been set to the length in R, which is 1 plus 1. R is the node that we're dealing with. And V and the path from R to V is has been incremented from 1 to 2, and moreover, V has been put on at the end of the Q. So we have finished dealing with R and have marked it as complete. I didn't mention that in figure C, after all that processing, W was marked as complete. Okay, so now we have T and X and V on the Q. We take T off the Q and we move to E and deal with what T is going to be understood to be connected to. So of course it's connected to W, but W is not undiscovered. It's connected to X, but X is gray, so it's also not undiscovered. And it's connected to U, and U has till now been undiscovered. Thus, we mark the T to U link in our tree, that arc. We set U's path length to T's plus 1, namely to 3. And we are done with processing T, and the Q has X on it from and V on it from before, and U at the end of it having just been put on as it was processed. We now again move on to the head of the Q, X, take it off, and look at things connected from X. Well, X is connected to W, but that's complete. X is connected to T. It was marked as complete in the previous stage. And so it's complete as well. And X is connected to Y. So we're going to deal with Y. We're going to put Y on the Q, leaving the Q with X off it and Y at the end, now being VUY, as shown in figure F. Moreover, the length of U is set to the length in T said that wrong. The length in Y is marked as the length of X plus 1, that is to say to 3. And having dealt now, and the associated gray, the associated tree nodes from X to Y is now marked. And having completed dealing with X, we mark X as complete. So the Q now, at the end of F, is VUY, and we take V off the Q. V is connected to only previously discovered nodes. In fact, to the one node, R, which is complete. And so there's nothing to put on the Q and no paths to mark. And V is just marked as complete, leaving U and Y at the end of stage G. We take U off the Q, we find that U is connected to T and Y, but both of them have been discovered. One's complete, one is discovered but not complete, gray. And so we mark U as complete, and we're done with that stage. And finally, only Y is on the Q. We take Y off the Q. As before, everything it's connected to is not undiscovered. In this case, they're both complete. X and U are both complete. So we can mark Y as complete. And now the Q is empty, and so the loop ends. Notice what the result is in figure I. If we consider S to be the root of the tree. S has two children. The arcs to it are the marked arc from S to R and the marked arc from S to W. R has one child. It has the path from R to V. If we want to get from S to V, we'll follow those marked arcs S to R to V. Now, S's other child, W, has two children along the marked arcs, namely T and X. And T has a child a child U with its marked arc, and X has a marked arc to its child Y. Notice that X is not a child of T, even though there is an arc from T to X, it's not marked, and likewise from U to Y. This breadth-first tree that we've been talking about, called pi, it defines a tree which can be seen in either order. If you start at the leaves of the tree, you get a path to the parent along the tree arcs, and then from them to their parents along its parent to parent tree arc, and ultimately back to S, and that gives you the path from any one of the nodes other than S, or in fact including S, back to S. Turned around, we see a tree rooted at S down to along all the paths that eventually get all the other reachable nodes. Notice that we have dealt with the nodes in this breadth-first order. That is to say, we have treated all the children of one parent node before moving on to treat its children, and in turn later its grandchildren, and so on. Notice that because the order in which we treat adjacent nodes that are undiscovered, that is to say, the children, determines the order in which the children and ultimately the grandchildren and so on are dealt with. There are multiple trees, so if we consider that very first consideration of the nodes adjacent to S, there were two possible destinations, and we said that they could have been taken in either order. What that basically means from the point of the tree is that one of them will be the first child, and the other will be the second child. And if we had happened to take it in opposite order, the children would have been swapped, producing strictly a different tree. Moreover, the whole business depends on which is the source node. You get a different tree for every source node. But when you take a particular order, you get a particular set of tree edges, that is to say, a particular tree, and then you have other arcs that weren't tree edges, and those are called cross edges. So putting this in notation, we have a graph G consisting of a list of vertices and a list of vertex-to-vertex connections. We have one vertex being the source S, and we have the predecessor subgraph of G, G sub pi, which has a collection of nodes and a collection of subnodes, and that predecessor subgraph is a breadth-first tree if we've done what we said we were going to do, that is to say, the predecessor subgraph consists of all the vertices reachable from S, and that there's a unique simple path without cycles. As we said, the edges in this E sub pi are called tree edges, pi being the tree. Let's analyze breadth-first search. The initialization involved marking all of the nodes as undiscovered. So you have to pass through all the nodes, and that takes, if capital V is the number of vertices, then initialization takes theta of V time. We put each vertex on the queue only once, and we take it off only once. And when we do this enqueuing and dequeuing, we take time theta of 1 for each. So the total queuing time is, for the capital V nodes, theta of V. Moreover, the adjacency list of each vertex is scanned at most once. We pass through all the edges only once. So and we at least only once if we don't have to look back at the edge from where it came. And if there are capital E edges in the adjacency list, the total number, each is only looked at once, so that takes time theta of capital E. And so the total running time of the algorithm is theta of V plus E, proportional to the number of vertices plus the number of edges, and also to the number of edges. But if there is at least one edge from every vertex, then capital E is at least as long as V, and we can say it's just theta of E. Let us return to the issue of the shortest path distances. we'll call the distance from S to V the shortest path delta of S of V. Reminder that we have intended to put that length delta of S of V in node V, in vertex V. Of course, if S is not connected to V by any path, its length was set to infinity in the initialization, and it has never been updated in this breadth-first approach, and so it remains as infinity. The breadth-first search method of pathfinding has been illustrated on undirected graphs, but it works equally well on directed graphs. So as we're moving from a node to other nodes in the breadth first order, we only follow outward arcs. That is to say, arcs that are directed from the node we're dealing with to other arcs. In any case, for either kind of graph, it's intuitively correct that the shortest distance length that the lengths that we have computed are indeed the shortest distance lengths. But strictly, we need to prove that property. These three lemmas, the three on this slide, allow you to produce an inductive proof that says that if you have all the shortest paths of length of some particular, up to some particular length, then you also have the shortest distance path for all the paths that are length 1 greater than. And these three lemmas, I more or less read them. And that says that if V is connected to U, that is to say, you have an arc directed or undirected from U to V, then delta of the length to get to V is at most 1 greater than the length to get to U, because it only takes one more step to go from U to V. The second lemma says that all the breadth-first search distances are not less than the shortest distance. Ultimately, we need to show that it's not greater than or equal, GVV is not greater than or equal to, but also less than or equal, that is to say equal to delta of S and V. And the final lemma says that whenever the Q contains a particular list of vertices, call them V1 to VR, where V1 is the head of the Q and VR is the tail, then everything on the Q has length given by these two relationships. That is to say, the element at the end of the Q is no greater than, yes, is no greater than the length at the beginning of the queue. Essentially because the only things we've put on have been things that were attached from the same parent. And also that each length is the vertices are on in order sorted by their lengths, D. That is to say, you can have, if two elements are adjacent in the queue, they can either have equal lengths or differ by 1. With those lemmas, we can prove now that the distances recorded are equal to the deltas. That is to say, the shortest distances. And this is the theorem that you then can prove, namely that our method produces distances d of v that are the deltas of S and V for every reachable vertex. And that the tree in question that we have developed gives us the paths from the paths that are the shortest paths. This is the end of the substance part of this first video on tree traversal. It was on breadth first search. Now, list of 2 worksheet questions that need to be passed in once you've completed listening to this video. We move on to an exercise that will be done in an inverted fashion in the class. The exercise that we'll do in class, that you'll do in class. There's a graph with 8 vertices, numbered 1, 2, 3, 4, 5, 6, 7, 8, of which the one index 3 will be the source vertex for your path length search. There are 8 edges, 1 to 2, and its symmetric partner 2 to 1, 1 to 3, 1 to 4, 2 to 3, 2 to 5, 3 to 5, 4 to 5, 4 to 6, 7 to 8, and for all of those, the symmetric partners. That is to say, the ones where the 2 indices in the pair are in the opposite order. With that vertex number 3 as the source vertex, use the BFS algorithm to find all shortest paths. You should, in your answer, give the order in which the vertices were taken off the queue. First vertex that's taken off, the second one that's taken off, and so on. You should also indicate which of these edges that were listed are the tree edges. And you should give the path lengths for all 8 vertices. Finally, for vertex 4, show what the successive edges are that traces the path back from vertex 4 to the source vertex 3.